Hi, in this video we are going to learn about how to use Plink to perform quality control in GWAS data analysis. So Plink is a software that can be used to perform all GWAS related activities, right from loading data, cleaning data, manipulating data, and performing quality control, and then eventually run the association analysis. So in this video, we are going to focus on first part of GWAS setup, which is how to read data, how to clean data, and how to perform quality control. So for this video, we are going to use same data set that we have used in SCAD data analysis by Dr. Wu. The dataset's name is Exome CHR22. So this file can be found under SCAD directory. So the first thing we are going to do is load existing Plink data into Plink. Plink can read different kinds of data set, different formats. So one of the most popular format is a text file. There are two text files that can be read together in Plink. One file is called PED file, another is map file. And these formats are easily converted to one form to the other form. For this particular data set, we have data in Plink's own binary format. For that, we have three different files with the same name but three different extensions. So you will find three files with the name Exome CHR22 and with extensions .bed, .bim, and .fam. To read data in Plink, on the command prompt you need to type Plink, and then depending on what kind of format you have for your dataset, you can use option called ---- file or ---- b file. Since this is a binary dataset that we are using today, we are going to use option called ---- b file, which tells Plink to look for binary format files. So the first command we are going to run is to read data in binary format and then recode data in text format. So to recode data into different format, the command is ---- So this ---- will convert data into a text format. Now the last option in this command is --out, which is very important option, and I will highly recommend you to use this in all your Plink commands. What it does is it creates all the output files that will be created by this command with this name. So here I'm using the same name, Exome CHR22, as out name. Now the output files will have same name but different extensions. So the way it matters why to use --out option is for a log file. Every time you run any Plink command, it creates a log file that stores information about what version of Plink you used, what time did you run the program, what were the options that were used in the command, and then details about the dataset. Now by default, if you don't use --out option, all the output files are created with name Plink. So the log file Plink creates is plink.log. Now if you don't use --out option, every time you run any Plink command, will create a log file with plink.log and every time you run new command, the old file will be overwritten by this new file. So you lose all the information of log files for your previous command. So using --out option, we'll save all those log files with appropriate names. So here is the first command that I'm going to copy and paste in the command prompt. So now Plink is reading that data set in binary format and it has recorded. The one thing I need to mention is I have all the input files in this GWAS Plink amid directory where I'm running Plink from. So keep all your data set in the same directory where you'll be running your Plink analysis in. That way you don't have to provide path for files. So anytime you run Plink, it shows you this information on your screen. A version of Plink and more information about Plink, and then it tells you a time and date when you started your analysis. It gives all the options that you have used in your analysis, and after that it gives you more information about your dataset as it reads dataset. So it's reading a map file and then telling all the information about markers. So it's telling that there are 16,885 markers read from the BIM file, and from the FAM file, which is family information in it, tells you all information about all the individuals in your dataset. In this particular example, we have 1092 individuals. And then it gives more information about your individuals and marker if it's available in your dataset. Like if you have binary outcome and if you have specified your case control status in your PEM and PET file, then it will tell you how many cases and controls there are, how many males and females there are. Unfortunately, we didn't have this information in this dataset. We have it in some other data format, and I'll explain that later as we proceed. So that's why Plink didn't have any information about how many cases and controls and males and females there were. And after that, it gives you more information about markers, and if we have certain criteria for markers to be included in dataset, it gives that also. So in this command we didn't specify anything. All we told was to convert dataset. So in last lines it's telling that it's writing the recorded files, and the names for those recorded files are exome.chr22.ped, and a map file is called exome.chr22.map. And then it tells you how much long it took to run the analysis and when it was finished. Now if you go back to your directory structures, you will see new files listed: exome.chr22.ped and .map. Now although this is a very short data set, a subset of typical GWAS data, you will still see that the PED file, which is a text file now instead of binary compressed file, the dataset size is much bigger than originally it was. So that's why the compressed file format is much more recommended than the text format, because as you go with the current data sizes where we have millions of markers and few thousand individuals in dataset, this file can easily go in hundreds of gigabytes. So that's why it's highly recommended to use Uplink's binary format, which is much quicker to load and analyze. So once we have converted data into different format, we can either use that converted format or the original compressed format. Now, as I said, it's recommended to use a binary format. So I'm going to use a binary format for our analysis today, but I just wanted to show you how to convert data from one form to the other one. In this particular example, we are not going to use multiple data set, but Pling can handle multiple data sets. It can merge multiple data sets together, and you can clean them. You can even change strands if you have to when you're merging data sets. So it's much more versatile tool. But for today's example, we just have one data set, so we are not going to merge multiple data set. So once you have data set in Plink, you can perform certain quality control checks. Now the very first one would be to check the missingness in your data. Now we expect data set to be mostly non-missing, and if there are particular missingness patterns, then we would go after them. And if we have particular SNPs or individuals with more than average missingness, then we might want to exclude them from our analysis or go back and check our data set if there is any kind of formatting error because of which we got missingness. So to do that, we need to look at missingness in our data both by SNP as well as individual. So the option that is used to calculate missingness in data is called --missing. So we again load data in Pling by the same command. So we call Pling by typing Pling. We read data by saying --b file, which is for a binary file. The name of our data set is exome chr22. And with the --missing option, we are asking Pling to calculate missingness in data. And as I said before, I always prefer to use out option, and I name files according to the analysis I am performing that Pling command. So in this case, I'm going to name all the output files as missing rate. So let's run this command and calculate missingness in our data. So it was pretty fast, being a small data set. And you will notice that the first part is almost the same as what we got in converting data from one format to the other one. The first part is always information about Pling software, the version of Pling software. In the options in effect part, now we have --missing because that's the option we provided to calculate missingness in data. And then it read the same file, so we should have same number of markers, same number of individuals. And after that, instead of writing different format file as before, this time what it's telling is writing individual missingness information in file called missingrate.ims. It's also writing a locus missingness information file called missing underscore rate dot lmiss. So these are the two files created, one for missingness by individual, other is missingness by marker. And for all these commands, it always creates a log file. So that's why I mentioned always give out name so that log file is not overwritten. So all the information you saw on screen is written in log file. So these are the two files, missing underscore rate dot lmiss, which is a missingness in data by marker. So we'll see that each row represents SNP. So we have chromosome name for that SNP, RS name. Then we have number of missing genotype. Then these are total genotype, and this is our missingness rate. So you'll see for almost for each SNP we have zero missingness. So it's very clean data where we don't have missingness. Also, if you look at the IMIS file, it gives you missingness, but now by individual. So your each row is representing individual, and you'll get the same columns, but now it will give missingness for each individual. And this being really clean data, we don't have any missingness. But typically you would see missingness pattern, and then later I'll show you how to exclude individuals or markers based on missingness threshold. So this is how we calculate missingness in our data. The next thing we want to check is the allele frequencies. Now, depending on the analysis we are performing, we might want to exclude certain SNPs with extremely small allele frequencies. So that's why getting idea of how many SNPs are below that threshold or overall distribution of minor allele frequencies is very important. So to compute allele frequencies, we again call plink, read the same data set, and now the option for computing minor allele frequency is minus fric. Now here I am giving one more option called -ind, which is a threshold I'm using for missingness in the data by individual. So what it means is I'm asking plink to exclude all individuals that have missingness more than 5%. So 0.05 is a proportion which corresponds to 5%. So I'm asking plink to read data, then exclude all the individuals that have more than 5% data missing, and then compute allele frequency. And my output file names I want for that are MAF. So let's run this command. Now again, the rest of the part would be same except for options in effect. we have additional minus minus freak in this case, and MIND. So the result of minus minus MIND you can find here. If you look at this second last line, it says 0 out of 1092 individuals removed for low genotyping. That's the criteria we used. If missingness was more than 5%, then we asked Blink to exclude those individuals. But this being really clean data, as we saw before, there were no individuals in our data set that had more than 5% data missing. So Blink did not exclude or remove any individual based on missingness. And then in the final line, Blink tells us that it computed allele frequencies and they are written in maf.fric file. So if we look at this new file, maf.fric, it looks like this. We have chromosome name, SNP name, we have two alleles, A1 and A2, and the way typically Blink does is it calls allele 1 for minor allele. So in this particular SNP, the first SNP, T is a minor allele, C is a major allele, and minor allele frequency is 0.0073, which corresponds to allele T. And if we just scroll through this, we see that there are so many SNPs with extremely low allele frequencies. Now another quality control check we want to do is for Hardy-Weinberg equilibrium. Now we want to use only those SNPs in our further analysis that are in Hardy-Weinberg equilibrium. So to perform Hardy-Weinberg test, there is option called minus minus Hardy that computes Hardy-Weinberg equilibrium p-value. And I am again using the same threshold for missingness. It's minus minus MIND. Now I know in this case there are no individuals that have more than 5% missingness. But if you have any, you can use this option every time you want to run any analysis, because you want to exclude all those people from all analysis. Now just using this minus minus MIND option in any of this calculation does not exclude those people from your original data set. It just excludes them from that particular command and excludes from that particular calculation. So you have to use this option in every command if you want to exclude those people from the respective analysis. So use this minus minus Hardy option, which will compute Hardy-Weinberg equilibrium p-value, and we want it to be written in file called HWE. So let's run this analysis. Okay, so the new output file Blink has created is hwe.hwe. So in the Hardy-Weinberg equilibrium output file, see that there is one row for 3 rows actually for each SNP, and if you look at the test column, it will say all, affected, or unaffected. So what Plink does is it computes Hardy-Weinberg equilibrium p-value for all individuals, and then only for affected individuals, and then only for unaffected individuals. But in our data set, we didn't have affection status, so Plink could not perform only affected and unaffected p-values. So that's why it's putting NaN here. But it did compute for all individuals. So you'll see for most of them the p-values are close to 1, except in few cases we see really small p-values. Now small p-value means it's far from equilibrium. Typically we have for GWAS a threshold of Hardy-Weinberg p-value as 10 to the minus 8. So some of the SNPs would be excluded if we have a threshold for Hardy-Weinberg equilibrium criteria.